All right, so welcome to the Set Theory Seminar. Yet again, our speaker today is Trevor Wilson from Miami University, which is not in Florida, as you might expect. I've wanted to hear from Trevor for the longest time. I had some opportunities. I tried inviting him to come to CUNY back when things were normal. It never worked out. So one way or the other, I am glad to finally get Trevor to be speaking at CUNY. And Trevor is going to speak today about the large cardinal strength of Vopenka's principle for trees and for rayless trees, a topic that I'm actually super interested in. So Trevor, we are all very glad to have you here. Go right ahead.
Thank you very much, Vika, for inviting me. I'm very glad to be here. Some background about Vopenka's principle. In this talk, we're going to work in some second order set theory just so that we can talk about arbitrary classes without assuming that classes are definable. But if you want to consider only definable classes, that's okay too. It's just a special case. So let me define Vopenka's principle. There are many equivalent ways to state it, but the one that I'm going to use in this talk is I'm going to call it VP omega, which is not standard notation, but it'll be convenient for this talk. That's Vopenka's principle for countable signatures. So that says that for every proper class of structures with the same countable signature, there's an elementary embedding from one structure in the class to another. And here countable signature means that there are countably many relation and operation symbols. Actually, most of the things that we considered in this talk, they'll be just structures with only relation symbols, in fact, very simple ones, namely graphs. But this is the general form. And I want to mention this VP omega, what I'm calling VP omega, is equivalent to Vopenka's principle for all signatures, which is VP. So why am I calling it omega? It's just this equivalence, it doesn't virtualize. So by that, I mean, it doesn't generalize to the case of generic elementary embeddings. If you put in the definition generic elementary instead of just elementary embedding. And uncountable signatures are just irrelevant to the talk. So I kind of want to simplify things by just only ever considering as much as possible structures with countable signatures. Now, okay, here's some more notation for particular instances of Vopenka's principles. I'm going to write VPXY to say that for every proper class of X, so some kind of structure X, there's a Y, some kind of morphism from one structure in the class to another. So really, this is a property of a category. X and Y are the structures and morphisms, but we don't really need to use any category theoretic terminology in this talk. Now, many instances of this VP for some category are known to be equivalent to VP itself, that is for all kinds of structures. So one example of this, a fairly recent example, it's an algebraic example, whereas the rest of the talk will be graph theoretic, but an algebraic example is that Vopenka's principle for abelian groups and non-zero homomorphisms. So that would say that for every proper class of abelian groups, there is a non-trivial homomorphism from one group in the class to another. Now, a fairly recent theorem of Adam P, I'm afraid I don't know how to pronounce this name, sorry, but about almost full embeddings of categories that implies that VP for abelian groups and non-zero homomorphisms is actually equivalent to VP itself. That is for all structures, which may as well be assumed to have countable signatures. So this was kind of surprising because previously abelian groups were considered to be very simple, especially simple structures, but then it turns out they're complex enough to capture the entire strength of Vopenka's principle. Now, so in this talk, though, instead of groups, we'll consider relational structures. So the case of one binary relation, in fact, is as complex as the general case. So namely, the following are equivalent. Vopenka's principle itself And Vopenka's principle just for structures with one binary relation, which you could call digraphs, with embeddings, not even elementary embeddings, just embeddings, meaning just an isomorphism to a substructure. So in other words, this principle here, VP substructures with one binary relation embeddings, it would say that for every proper class of digraphs, one embeds into another. One's isomorphic to, you can find a copy of one inside another. So if you have enough digraphs, then they start to look similar in the sense of embeddings. Now, in fact, you don't even need directed graphs. So among structures with one binary relation, it suffices to consider just symmetric irreflexive relations, so which we'll call graphs, meaning undirected graphs without loops or multiple edges. So in fact, the following are equivalent. I should mention, who are these equivalences due to? I forgot to put that in here, but I think that the stuff on this slide is due to Hederlin and Poulter. So the following are equivalent to Vopenka's principle itself and Vopenka's principle just for graphs and embeddings. Then you might ask, well, what about specific kinds of graphs? Limiting it even further, do you still get equivalent principles, or do you get something weaker than Vopenka's principle? Weaker in the sense of, well, just in the sense of logically weaker, but then if you do, then you can think about what is its large cardinal strength in terms of the large cardinal hierarchy, and analyze that for various specific kinds of structures, such as specific kinds of graphs. Now, I'm sorry, I have a couple of questions for how the screen sharing thing works. First of all, can you guys see where my pointer is on the screen?
Yes.
Okay, good. And then I have another question about annotating, because I couldn't get this to work when I was testing it right before. Can you see that I'm scribbling on the screen? Okay.
Yes.
Great, thank you. Okay. Yes, because I'll want to scribble a bit in the future. So yeah, what about specific kinds of graphs? Well, one important kind of graph.
The only annoying thing, Trevor, is that when you scribble on one page and you move to the next, the same scribble is still there.
Oh, I see. Okay, so it's gone now?
Yes.
Okay, good. Thank you. Now, a specific kind of graph that we might want to consider is a tree. That's a particularly simple kind. So that's a tree in the graph theoretic sense is a connected acyclic graph. So it's a graph with a unique path between any two, I said points, but I mean vertices. So if a graph has a unique path between any two vertices, then it's a tree in the graph theoretic sense. Now, how does that relate to the set theoretic sense or the order theoretic sense? Well, if you choose a root for the tree, then it becomes a set theoretic tree of height less than or equal to omega, where the order in the tree order is a vertex u is less than or equal to a vertex v. It means that u is on the path from the root to v, so the unique path. Okay, so you can, if you want, actually just replace tree with ordered tree in the talk, and then everything works pretty much the same. It's just that I feel like trees in the graph theoretic sense are slightly simpler, and I mean it's just a connected acyclic symmetric irreflexive relation. So okay, that's actually 4 adjectives. Is it really simpler? I don't know, but I felt like I wanted to consider graph theoretic trees. Now, I'm sorry, I don't know if you can hear those dogs. They're not my dogs. Hope they'll be quiet soon. So what is the large cardinal strength of Vopenka's principle for trees? I think is a natural question if you're considering special kinds of graphs. But before talking about large cardinal strength, I should say, first of all, what is the large cardinal strength of Vopenka's principle itself, well, that was determined by Solovey, Reinhardt, and Kanamori. She showed the following are equivalent. Vopenka's principle, equivalently just for countable signatures, like I said, is equivalent to this existence for every class A of an A extendable cardinal. And you could also say the existence for every class A of an A supercompact cardinal. I just wanted to pick, I mean, that's not equivalent for a particular cardinal, but it's equivalent, the overall statement is equivalent, but I just wanted to pick one of them to use as a characterization in this talk. So we'll look at A extendable cardinals, which I'll define on the next slide, which will give the large cardinal strength of Vopenka's principle itself. And then we'll see, well, how much weaker is it, if at all, if you limit it from all graphs just to trees. So the cardinal kappa is called A extendable if for every lambda greater than kappa, there's a theta, and there's an elementary embedding from V lambda with a predicate for A to V theta with a predicate for A, and the critical point is kappa. The A extendable cardinal is the critical point of these things. And I should mention, because this becomes important later, that in this definition, we omit the condition, the usual condition, or at least, I don't know, at least half the time people include the condition J kappa greater than lambda. So it's saying that the critical point maps above the height of the domain structure here. Now, omitting this might lead to a conceivably weaker notion, which we'd call weakly A extendable, except it's known to be equivalent. However, I don't want to rely on that, because the equivalence of those uses Kunin's inconsistency or something along those lines is necessary to use. And that means that it doesn't virtualize, well, simply because virtual Kunin's inconsistency isn't actually inconsistent. So in the virtual context, we'll need the word weakly to mean that we omit this condition on where the critical point goes. It might not map up above lambda. In fact, in the virtual setting, it could even, lambda could even be a fixed point of the embedding. But in the original non-virtual setting, then it's equivalent. Okay, so those are A extendable cardinals. And so the virtual version of this was defined by Vika and Joel, and it says the cardinal kappa is weakly virtually A extendable if for every lambda there's a theta and now a generic elementary embedding from V lambda with a predicate for A to V theta with a predicate for A and a critical point kappa again. And so generic elementary embedding here just means that the embedding exists in some generic extension. And it might as well be in the generic extension where the domain is collapsed to be countable. That's enough to pick up such a thing if it exists anywhere by an absoluteness argument. Once the domain is countable, then J is a branch through a tree essentially. So then you can use an absoluteness argument. Now, even though J is generic, I should mention here, so V lambda and V theta mean the V lambda of V and the V theta of V. So they're rank initial segments of the ground model. And weakly here, it means that, as I mentioned, we don't require anything about the critical point. And so it could just move kappa up a little bit compared to lambda. In fact, it could be that theta equals lambda and J kappa is less than lambda. So in the virtual case, it's quite a bit different. There's more freedom sort of, and we don't want to require anything about where the critical point goes, except of course that it's greater than kappa. Now these cardinals, weakly virtually extendable cardinals can exist in L. In fact, they do if zero sharp exists. Basically you just shift, say kappa is the least indiscernible, and you shift all the indiscernibles up by one, and then you can, or maybe the first omega indiscernibles up by one, and then by an absoluteness argument, you can pick up such a J. I mean, the embedding from 0 sharp itself doesn't exist in L, obviously, but you pick up in L some J which resembles it. Okay, so those are weakly virtually A extendable cardinals. And then those are going to correspond to a generic version of Vopenka's principle by basically a virtualization of the Solovay, Reinhardt, and Kanamori result. So the definition of generic Vopenka's principle is GVP is generic Vopenka's principle, which says that for every proper class of structures with the same signature, there's now a generic elementary embedding from one structure in the class to another. So that the generic, of course, corresponds to this G here. Could be called virtual Vopenka's principle, but it was originally called generic Vopenka's principle. And so Vika and Joel showed that the following statements are equivalent. GVP, generic Vopenka's principle, is equivalent to the statement that for every class A, there's a proper class of weakly virtually A extendable cardinals. Now, I should mention, so back in the result of Solovay, Reinhardt, and Kanamori, I just said for every class A, there is an A extendable cardinal, not necessarily a proper class, but it's not hard to see actually that if this is true, you can equivalently get a proper class of them. But in the virtual setting, that's not true. So we have to be a bit careful. So in the virtual setting, you have to assume a proper class of weakly virtually A extendable cardinals in order to deal with arbitrarily large signatures of the structures, as in the definition of generic Vopenka's principle here. Basically, if the signature has, if you have like alpha many relation symbols, then you would need a weakly virtually extendable cardinal above alpha. All right, so in this talk, though, I wanted to talk mainly about structures with countable signatures. So there's a slight variant of this result, which is proved in exactly the same way, which says, so if we define GVP omega to be a generic Vopenka's principle for countable signatures, so for every proper class of structures with the same countable signature, including, say, graphs or trees, but also things with multiple relation symbols, say. So then there's a generic elementary embedding from one structure in the class to another. And so just a variation of the result I just mentioned says that the following statements are equivalent, GVP omega, so for countable signatures, and for every class A, there is a weakly virtually A extendable cardinal. So we just say that there's one. I mean, actually, if there is one, then you can see by like varying A a little bit, then you can get more than one, but it could be that they're bounded in this case, in the virtual setting. So yeah, so I should mention that generic Vopenka's principle for countable signatures, and then for all signatures, they're equiconsistent, but they're not equivalent, like in the original non-virtual setting they were. So why are they not equivalent? Let me just say one thing about this so you can think about it if you want, but we're not going to use it, but in the talk. But if you consider the case where there's an omega Erdős cardinal and there's no inaccessible above, well, an omega Erdős cardinal, just a single one, that's sufficient to get GVP omega. Whereas if you had GVP for all signatures, you could fairly easily get a proper class of inaccessible. So if there's no inaccessible above your omega Erdős, then you don't have GVP. So that's how you can separate them. Okay, so now we do have to start observing the distinction between the countable signature case and the general case. Now, I'm sorry, but if I give you just a moment, I have to get a drink of water. Should have done that before, sorry. And by the way, please feel free to interrupt me with questions at any time. Yeah.
Why are they equiconsistent? Sorry,
Oh, why are they equiconsistent?
I got lost there for a second.
Okay, because, well, I didn't actually mention why. So I mentioned here that an omega Erdős is sufficient to separate them, but it's actually necessary also, because if you have GVP omega and not GVP, and then you can show that there are that basically the embeddings witnessing GVP omega have fixed points. And so if you have, and then you can show if GVP omega is witnessed by embeddings with fixed points, then you can use that to show that the fixed points are, well, that they satisfy a partition property.
Yeah, a rank into rank, and that gives a proper class of the virtually extendables, right?
Yeah, yeah. Well, yeah. So you can get a proper class of virtual rank into rank cardinals, but in fact, you can get a proper class of, like, I guess you could call them boldface virtual rank into rank cardinals, meaning that you can preserve any predicate you want, and so that's equivalent to being omega Erdős.
Yeah, I see. I got it now. I figured it out. Thanks.
Great. Okay, so now I can state the first of the two main results that I want to discuss in the talk, the two results mentioned in the title and abstract. So it's that the following statements are equivalent. Well, basically, it's determining the large cardinal strength of Vopenka's principle for trees. And you could say that it's equivalent to weakly virtually A extendables, or you can just say equivalently it's equivalent to GVP omega. So that, I think I made a different decision in the abstract, but in the talk I want to say VP for trees is equivalent to GVP omega. So this shows the two different ways to weaken Vopenka's principle are actually equivalent. So the first way would be to weaken it to generic Vopenka's principle. So to allow the embeddings to exist in a generic extension. Another way would be require still the embeddings to exist in V, but require the structures to be simpler, so namely to be trees. Okay, so it's not too surprising, I think, that what this shows is that Vopenka's principle for trees is much weaker than Vopenka's principle even for graphs. It's not surprising just because trees are especially simple kinds of graphs. But as far as I can tell, nobody really considered the large cardinal strength of Vopenka's principle for trees at all, which is fortunate for me, I guess. But it turns out it's not actually that difficult to prove this. So in the talk, I'll pretty much give a complete proof of this and then go on to the second result that I mentioned in the abstract. So before I start proving it, let me just say a little bit about how you might hope that the proof might go. So if we could show that the existence of embeddings between trees was generically absolute, then one would imply two just immediately, just because then the generic part would be superfluous. You could get the embeddings just in phi by absoluteness. But unfortunately, the existence of embeddings between trees is not generically absolute. Trees are not quite that simple, at least not with respect to embeddings. Because you could consider like an Aleph-1 star. So that is, okay, let me try to draw a picture now. So a star means you have a central vertex and, oh, sorry, my handwriting is very bad with the mouse here, but then you just have many radial edges here, Aleph-1 of them, and then an Aleph-0 star, same thing, but with Aleph-0 radial edges. Okay, so there's no embedding between them. but there is, and in fact, they become isomorphic if you just collapse Aleph1 to Aleph0. Okay, so the existence of embeddings between trees is not generically absolute, but we should still keep in mind maybe trying to show some kind of generic absoluteness when we want to show that 1 implies 2 here. Okay, so how are we going to show 1 implies 2? Actually, meaning GVP omega implies Vopenka's principle for trees. So you take a proper class of trees and you want to embed one of the trees into another. And okay, so we're going to add some additional structure to the trees. Well, first of all, we're going to turn them into rooted trees. That's usually more convenient when you get into the details. So for each tree in the class, I'm going to call a tree like script T, and then its set of vertices T, and then ET is the edge relation, the adjacency relation. And okay, choose a root R and a relation which well orders the set of children of each vertex. So this is not the tree order at all. It's almost, I guess you could say, orthogonal to that. It's so if you choose a root, then you have a notion of children of a vertex. That means the ones that are adjacent to it in the direction away from the root. And we want to well order the set of children. So we want to say like which sibling vertices are older and which siblings are younger. And so if you expand the trees that way, you can apply a GVP omega to the expanded trees, and you get 2 of them, and in some generic extension, an embedding from the first one to the second one, preserving all the structure. So in particular, these well orderings. For each vertex, the well ordering of its children is preserved. So in a sense, it's an order preserving embedding of trees. So we're going to show that the existence of order preserving embeddings of trees is actually generically absolute. And then that has a consequence which is stronger than what we wanted to show, because order preserving implies injective. Okay, so how are we going to show this absoluteness? So we want to get some kind of approximation to J in V, even though J itself is in a generic extension. So going along in the tree, for every vertex V, we take a condition PV, which decides the value for where V goes. And say J0V is the value of JV that's decided by this condition that we associate to V. And so we go along in the tree by recursion on the level, and then when we want to deal with the children of each node, then we go by recursion on this well ordering, which we chose. Now, so we do this in such a way that the order of these conditions should reflect the tree order. That is, if you have one condition deciding where a vertex V maps to, then the conditions deciding where the children of V map to ought to be stronger than that one. So as you go down, or I guess go up a branch of a tree, then the conditions get stronger and stronger. But the conditions deciding where 2 siblings go may be incomparable. Okay, so doing that will imply that the map J0 will preserve the tree structure. That is, it'll be an embedding of trees. Well, no, sorry. That alone implies that it'll be a homomorphism of trees. But we need to show that it doesn't collapse. It doesn't send 2 siblings to the same vertex. Okay, how do we ensure that it doesn't do that? Well, we can choose each condition to minimize where it sends the associated vertex with respect to this order while preserving the order. So basically so when we're dealing with the children of one vertex, we send each one to the least place it can go, which is greater than all the things that it's supposed to be greater than. That is, it's greater than where all its younger siblings mapped to. So we just kind of we ensure the order preserving property as we go along. And so the point of introducing the order is that it works to preserve, it works to maintain order preserving property as you go along, whereas it would not work in this situation to maintain injectivity as you go along. If you try to do that, you could run out of room. But if you try to do this, you don't run out of room, because at every step, your J0 will be pointwise less than or equal to J. So you always have enough room. And so then this J0, like J, it's an embedding from S to T, but unlike J, it's in V itself, which is what we wanted. I mean, it preserves this order, which we ultimately didn't care about. We only needed injectivity, but strictly order preserving, preserving the strict order relation implies injectivity. So injectivity is kind of a shadow of the order preserving property. And that's what we wanted to get, was an embedding, actual embedding in V between two of these trees, S and T. So that's the proof of one implies two. And next, I want to say how to prove the converse. So Vopenka's principle itself, but just for trees, implies generic Vopenka's principle, but for all structures in countable signatures. Okay, so to prove that, instead of proving it directly, it's useful to take a detour through labeled trees. In fact, in a sense, most of the results I'm talking about today could be, or most of the techniques that I'm talking about naturally apply to labeled trees. It's just labeled trees are kind of more technical. So I thought it was more interesting to state results for trees themselves. But in some sense, when you get down to the nuts and bolts, kind of labeled trees are the natural things to work with. So for a set X of labels, an X labeled tree is a rooted tree with a labeling function. It sends each vertex to a label. It assigns to each vertex a label. So in other words, okay, here's the tree. And then we could label it with maybe these vertices are labeled with stars, and these vertices are labeled with hearts, or if you wanted it to be boring, you could label the vertices with the numbers 0 and 1. And so we'll show in the course of proving the theorem, a larger theorem with more equivalences, which is that in addition to 1 and 2, also statements 3 and 4 are equivalent. So also Vopenka's principle for two labeled trees is equivalent to just Vopenka's principle for trees. And also Vopenka's principle for two labeled trees just with homomorphisms instead of embeddings is still equivalent. I should say something about what a homomorphism is, though. So when dealing with labeled trees, it's going to be convenient to require homomorphisms to preserve the level, which is the distance from the root, as well as the labels naturally, and as well as adjacency naturally. So let me try to draw like an example of a homomorphism of labeled trees. Would be like, oh, actually, I can just add a little to this example. So this admits a homomorphism that was supposed to be an arrow, sorry, to this tree here, where you have like so, and then these two nodes down here get sent to the same one over here. Okay, so the crucial distinction from embeddings is they don't have to be injectives. And so you can send two siblings, let's say the middle one here is the root. So these two nodes labeled with hearts are siblings. You can send two siblings to the same one as long as they have the same label. Okay, so this would be an example of a homomorphism. Okay, so what we showed on the last slide was that 1 implies 2 here. And 3 implies 4 is obvious because every embedding is a homomorphism. So now if we want to complete this, going around in a circle, we can show 2 implies 3. That is VP for trees can be kind of beefed up to VP for 2 labeled trees. And then 4 implies 1. So that is that VP for 2 labeled trees and homomorphisms is equivalent to GVP omega. And by the way, in a sense, the most fundamental thing here, or the most basic thing, is the 1 and 4 are equivalent. So although it seems like a more technical statement, but I think that's the most basic thing that's going on here, is that GVP omega is equivalent to VP for 2 labeled trees and homomorphisms. It's just that both 2 labeled trees and homomorphisms of such are more technical seeming, but so I didn't lead with that, but I think that one if and only if 4 is kind of the most basic thing that's going on here. Okay, but so we're going to show 2 implies 3 next. And so that means that VP just for trees is implies VP for 2 labeled trees. So if you have a proper class of 2 labeled trees, we want to reduce this just to the case of trees. So for each 2 labeled tree, we want to get a tree that's not labeled, but somehow encodes the labels. So we define an ordinary tree from our labeled tree as follows. So T is our labeled tree. So you subdivide it by replacing each edge with a path. So say you start with this labeled tree. I'll add some labels. And so we want to replace each of these edges with, well, you can think of first making the edge longer, although that doesn't really mean anything, but then adding some intermediate vertices. And okay, so that's what I mean by subdivide. And then we're not allowed to use the labels here. We want to get an ordinary tree, but we have to code that information somehow. And so we're going to do that by attaching certain leaves to the new vertices, the kind of intermediate ones along each of these paths that replaced an edge. And the leaves that are near an old vertex will indicate some information like what its label was and whether it was the root or not. So like in this case, we could say if a node is labeled with the heart, then you indicate that by adding a leaf, adding leaves at distance attached to the nodes of distance 2 from that guy in every direction. So like this. And like that. And whereas if it were labeled with a star instead of a heart, then you just put those leaves in a slightly different place to record that fact. And you can also indicate with this method where the root was. Since labeled trees we defined to be rooted. So now by our hypothesis of VP for trees, there's an embedding from, so on the left, this was U or T, and on the right it's U star or T star. So there's an embedding from one of these starred trees to another, okay? But that corresponds to a labeled tree embedding. Basically, the presence of these leaves in the right places ensures the label preserving property. These little leaves have to have somewhere to go, so they can only map to, I mean, you have to check some details here, so I won't say anything more about that. But anyway, this is how we reduce, in the case of two labeled trees, to just trees, is by subdividing them and adding leaves in certain places to serve the purpose of the old labels. So that's 2 implies 3. And then we have one more.
I have a quick
Yeah.
question. When do you have to add any edges to like that top to show that the top part there? Do you have to add edges so you can add some leaves so that you remember that was?
You have to add. There's a kind of problem here because I was too lazy to actually subdivide it enough. There should be 9 of these at least intermediate vertices here. Well, let me just extend it and add a bunch more. So like here for the, we said that for hearts, it was distance 2. So, okay, I've kind of messed up the picture a little bit, but say here's the one at distance 2. So we would just add a leaf here to indicate that. So it's, so we just subdivide with paths of length 9. And then in this case, we only needed a single leaf to indicate the label of this heart, whereas here we use 3.
Okay. And 9, I don't see exactly what's 9, but.
Well, okay. So if we only had to code 2 labels and not code where the root was, we could get by with 7. And the reason, well, let me just mention one reason why it's not lower. So you don't want to add a leaf here just because then you end up with something on the end like this, and you can't tell which one was the old vertex and which one was the new vertex. So you have to be a little careful about not adding leaves too close to, they're really 2 kinds of leaves, right? I mean, some leaves could come from the original tree and then some are things that you're adding. So you have to distinguish them somehow by leaving a little room.
Thank you.
And presumably the 9 is there to make sure that you've got enough unused subdivision vertices so that what you're doing near one vertex of the original graph and what you're doing near an adjacent vertex of the original graph are not running into each other's way or confusing you about which goes with which.
Yes, exactly. So yeah, we want the label of a given old vertex to be indicated by leaves that are closer to that old vertex than to any other old vertex. Yes.
So would this work for a higher number than 2 also? You would just leave more, add more points in between? Or? That's
right. Okay. So how I got from 2 to 9, I guess, was I added 1 to get 3. So like another label to indicate the root. And then I multiplied 3 by 2 and added 3. So yeah, for for another label, for a third label, you need 11, I think.
Okay.
And so forth. Okay, so now for 4 implies 1. So we want to show that Vopenka's principle for 2 labeled trees and homomorphisms implies GVP omega. And this is the method I'm using here has been used in other contexts, but I think not for Vopenka's principle, but it's used like in a paper of Eklof and Shalah, I believe, that also dealt with 2 labeled trees, or sometimes called 2 colored trees. I forget what they called them. Anyway, so if we have now a proper class of structures with the same countable signature, C. So for each of those structures, okay, I denoted it as if it were a relational structure. It doesn't really matter, but you have countably many, say, relation symbols. And then you can define from that, I'm going to work with the 2 to the omega labeled tree, which is not what we ultimately want. But for now, we define a 2 to the omega labeled tree. TA, it's, what I mean here is the underlying set is a to the less than omega. So the nodes of the tree are finite sequences, finite tuples from the structure with the usual tree structure, just meaning that each finite sequence is adjacent to its one point extensions, and also to the thing that you get by chopping off the last element if it has one. Now, so we have to make it a label tree though. And the labels are where you actually encode the structure, the relations R1, R2, et cetera, right? Because there's no real, the tree structure here is actually kind of trivial, right? It's the full array tree, I guess you could call it. The labels are where the information is. So each vertex is labeled with its type in the structure. So you could call these you could call these type trees. And the type is naturally coded as an element of 2 to the omega because the signature is countable, right? So meaning that also that the first order language here is countable. So we just label each finite sequence of elements of the structure with the set of all formulas with n free variables that it satisfies. And so doing that, you get a 2 to the omega label tree. But you can actually show that just 2 labels are sufficient in place of 2 to the omega. Well, how do you do that? It's just a matter of where you record the information. And this technique here, which I won't really discuss actually the details of, was used by Rowbottom in proving some things about partition relations. So I don't know if that's the first place it was used, but basically you can just kind of stretch out where you code things. So you can continue coding the formula is satisfied by a length n sequence. You can continue coding them later and interleave things. And okay, I don't want to say too much about how you do that because it's kind of a standard trick. But you can get a 2 label tree that just codes the same information, codes the type tree in just a slightly more complicated way. And so then by Vopenka's principle for 2 labeled trees and just homomorphisms is all we need here. There's a homomorphism from some TA at the type tree of some structure A in your class C to the type tree TB of some structure B, which was in your class C. So A and B are structures in C, the class. Okay, so now let's think about what a homomorphism of the type trees is. You can think of it as a tree of finite partial elementary embeddings from the structure A to the structure B. Why is that? Because a homomorphism sends an n tuple in A to an n tuple in B of the same type. So you could think of that as a finite partial elementary embedding. And then you have a tree of these things ordered by which finite partial elementary embeddings extend which others. It's, well, okay, technically a node in H is not just a finite partial elementary embedding because it also comes with an ordering of its domain and range, but I'm being a little imprecise here. But anyway, since the vertices are finite partial elementary embeddings, the branches are countable partial elementary embeddings from A to B. But if you collapse A to be countable, the same reasoning still holds, but now some of the branches are total, meaning you can go along a branch which just enumerates generically all elements of the domain structure A, in which case the homomorphism tells you how to map all elements of A to elements of B in a consistent way, well, in an elementary way. So then when you collapse A to be countable and then look at a generic branch in the type tree enumerating all elements, it gives you an elementary embedding into V.
A question.
Yeah.
Would it work if instead of collapsing it, you just forced with the tree itself? Same thing.
Yeah, I believe that would be the same thing. I have to make sure, but that sounds like the same thing. Okay, so now for further results, so I mean, this finishes the proof that all four of these things here are equivalent. You could put in some more other equivalent things at this level, but next I want to go to a different level of large cardinal strength and prove something there. So a lower one, in fact. So as I mentioned, trees are a especially simple kind of graph. So what's an especially simple kind of tree? Well, a rayless tree, that would be a tree without any infinite path. I'm talking really about graph theoretic trees, right? But if we choose a root, then without an infinite path is equivalent to saying without an infinite branch. And where a branch is just a path beginning at the root. So this would be equivalent to saying just a tree without an infinite branch. Now, the rayless trees are, you can also define them in a bottom-up way, that the trees that can be built up from nothing, from the empty tree, by transfinitely iterating the process of taking existing rayless trees, and maybe I'll draw a picture here. So like here's one rayless tree, just a single vertex. Here's another one. And so we take this set of two existing trees, and then we can add a new vertex up here and connect it with an edge to each of the existing trees, connect it anywhere you want, maybe like there, and then you get a new rayless tree. We could have done that with infinitely many. Okay, transfinitely iterating that process gives you all the rayless trees. So, I mean, these are now especially simple, and you have a technique for proving things about them that only applies in the rayless case, namely by transfinite induction following this construction of them. So that explains why you might expect VP for them to be weaker. Now, to determine the large cardinal strength of VP for rayless trees, we'll need to define, well, what it is that we're going to ultimately show that it's equivalent to. We're going to need a weakening of what I called weakly virtually extendable, which is weakly virtually strong. And we're going to need a weakening of GVP omega, which is GWVP omega. The W stands for weak, but it's a different kind of weak than in weakly virtually extendable and weakly virtually strong. There are just too many different ways to weaken Vopenka's principle, so the notation gets confusing. But fortunately, the concept maybe doesn't get confusing, because it turns out that many of the different ways to weaken it are in fact equivalent. So you only end up with just a few, in fact, 4 weakenings along the lines discussed in this talk, which I'll summarize at the end. So before defining a generic weak Vopenka's principle, let me define weak Vopenka's principle. Actually, in the non-virtual setting, the omega here is not necessary. So weak Vopenka's principle for countable signatures says for every sequence of structures, the main thing to draw attention to is this part here, this hypothesis. So if for any two ordinals, there's a unique homomorphism going backward, so from the later structure to the earlier one. So if you always have these backward homomorphisms, then there's a forward homomorphism from some A alpha to A beta. So that part is not the part that's new. The part that's new is this hypothesis. So without the hypothesis on backward homomorphisms, then this would just be Vopenka's principle. Because it turns out in Vopenka's principle, you can always take the homomorphism to go forward if you want. And that also, the hypothesis has to talk about homomorphisms and not embeddings, because the backward homomorphisms typically cannot be embeddings or even injective, because the later structures A beta are typically larger than the earlier structures A alpha, so you can't expect them to inject into earlier structures. So we really have to talk about homomorphisms here. So that's weak Vopenka's principle. I'll also remind you of it on the next slide. So a remark that may help to understand weak Vopenka's principle, although we don't really need it, is, so you could ask, I'm just restating it here, you could then ask, why is it a large cardinal axiom at all? So if you think of large cardinal axioms as strong axioms of infinity, well, you can, the first thing to note would be, does it even imply the axiom of infinity? That is, or greater than omega? Well, it does, because otherwise we have this sequence, we have an omega length sequence of structures, namely just the unital rings of the integers mod 2 to the n for various n. So that would be a counterexample, except that its length is only omega. It'd be a counterexample because that for n less than or equal to r, there's this unique homomorphism going backward, right? You just reduce modulo 2 to the n. But if n is less than r, there's no homomorphism going forward, no unital ring homomorphism going forward, just because 1 has to map to 1, 2 has to map to 2, and so forth, and then you get a contradiction if n is less than r. So this kind of algebraic example doesn't really have anything to do with anything else in the talk, but it kind of gives you a flavor of how weak Vopenka's principle works, I guess. Let me mention, again, this is not really necessary, not really basic for this talk, but the large cardinal strength of weak Vopenka's principle is that for every class A, there's an A strong cardinal. You could also call this word is wooden. And so then let me just remind you of what A strong means. But I stated it a little bit differently because we're going to virtualize it. And sometimes things that are equivalent in the ordinary case are not equivalent in the virtual case. So I want to state it in a way that gives what we want when we virtualize it. So we can say the cardinal kappa is A strong if for every lambda greater than kappa, there's an elementary embedding from V lambda with a predicate for alpha to something, some structure, which is an end extension, a transitive end extension. Here being an end extension is actually automatic because the domain is a rank initial segment of V. But anyway, it's an end extension of the domain. Codomain's an end extension of the domain, and the predicate A star agrees with A as much as it makes sense. So the main point here in any way that you want to define A strong is that J coheres with A up to any given point. And then of course the cardinal kappa we're talking about is supposed to be the critical point. Okay, so this is one equivalent definition of A strong. And I'll mention that we omit the usual condition J kappa greater than lambda here because it's not relevant to the talk. I mean, in general, it's not relevant to Vopenka's principle type things. And so we might call the resulting notion weakly A strong, except again, it's known to be equivalent. But again, the equivalence is proved using Kunin's inconsistency or something like that. And so you can't virtualize it. And in the virtual context, we'll use the word weakly to mean that you don't assume J kappa maps above lambda. Okay, so if in the virtual setting, we define the corresponding notion weakly virtually A strong to be, it starts out the same, but what's the codomain? So here we just say that M, and not necessarily the true membership relation, is an end extension of V lambda with the true membership relation, and its predicate agrees. So J coheres with A up to lambda. And J, of course, is just required to be generic here. That's what is meant by virtual. But V lambda is the direct initial segment of the ground model. And okay, so the main thing to point out here maybe is that we do not require the codomain to be well-founded, or even in V. But anyway, that's why I said epsilon star here. So it turns out that requiring well-foundedness would make the definition of weakly virtually strong too strong. It would become equivalent to weakly virtually supercompact, also known as weakly remarkable. And again, weakly means the thing about J kappa versus lambda. So people have, so I'm not sure who first noticed that, maybe Ralph Schindler, have noticed that this equivalence here, and maybe just said something like virtually strong is equivalent to virtually supercompact. But if you ask me, that just means that we have the wrong definition of virtually strong. It needs to be weakened so that it's weaker than virtually supercompact. So that's what I've done here, is by not requiring the codomain to be well-founded, that's the appropriate way to weaken it, so you actually get something weaker than virtually supercompact, which is then what we'll need for these results about Vopenka's principle for rayless trees. Okay, so now generic weak Vopenka's principle is, we're just combining the generic, we're just combining generic with weak in the obvious way. So we just talk about generic homomorphisms, right? That's the generic part. And then we have this hypothesis here, and that's the weak part. Okay, so just combining them in the obvious way. And then the following theorem is proved similarly to the non-virtual version. Similarly, once you realize that well-foundedness isn't needed or even desired, and Vika and Dan Nielsen worked out the details of this, I think, basically under slightly different definitions. So I just noticed that this was in Dan's thesis, and I didn't really read it carefully yet. So the definitions are all kind of different, but I think they essentially also proved the thing that I'm using in this talk, which is that generic weak Vopenka's principle for countable signatures is equivalent to the existence for every class A of a weakly virtually A strong cardinal. Is this more or less what you guys proved?
Okay, so the way that it worked was I think that you definitely had it figured out, and we didn't. We were trying to show that the two notions were actually equivalent. What we kept failing on was the well-foundedness of the target. So it was sitting right in front of us until I wrote to you and you told me your result. And then I was like, well, it's obvious. But none of it was obvious to us before I had your email. We were trying to show the wrong thing all along.
Okay, yeah, thanks
So
for refreshing my memory there.
Yeah, that is the history.
Okay, so now this is the kind of fourth level of large cardinal strength that we consider in this talk. So if you weaken Vopenka's principle in these two ways simultaneously, then that's equivalent to the existence of weakly virtually A strong cardinals. Okay, so but then now we're going to relate this to rayless trees. Okay, so and recall, just for comparison, the first main result I mentioned is that the generic Vopenka's principle is the same as Vopenka's principle for trees. And now the second theorem, the second one mentioned in the title and abstract, is generic weak Vopenka's principle is equivalent to Vopenka's principle for rayless trees. So in particular, VP for rayless trees is weaker than for trees, just because generic weak Vopenka's principle is weaker than generic Vopenka's principle. That part is not too surprising. What was a little bit surprising to me at first is, why does this weak here correspond to this rayless here? It's not really obvious that there would be any connection. So that part is maybe the only surprising part of this theorem here. And so this theorem is what I'm going to sketch the proof of next. Now, to prove one implies two, one that's generic weak Vopenka's principle implies VP rayless trees, it's more convenient to use the large cardinal hypothesis that, as I mentioned, is equivalent. So assume for every class A, there's a weakly virtually A strong cardinal, and then we'll show Vopenka's principle for rayless trees. So take a proper class of rayless trees and take kappa weakly virtually C strong, where C is the class. And then, okay, which tree do we want to consider? Basically one corresponding to kappa. So just take T, a tree, a kappa least rank in C. The point is that this tree will be moved whenever a kappa is the critical point of something. And then take a lambda greater than the rank of this tree. And so just its rank as a set, but actually you could say its rank in terms of the rank analysis of rayless trees that I mentioned, that would be more or less equivalent and it would also work. So then there's a generic elementary embedding into an end extension, as in the definition of weakly virtually A strong. And then the important thing again is this coherence, right? I mean, basically the definition of weakly virtually A strong, the central thing is the coherence, and then you just kind of want to make the rest of the definition as weak as possible, so that, but still being able to talk about coherence. Okay, so then by elementarity, it suffices to show something in the codomain, right? So it suffices to show that in the codomain, the structure M thinks that there's an embedding from T to J of T, because it thinks both of those are in the class C star. So, okay, it's important to note that the original tree is in the well-founded part because it's in V lambda. But J of T might be above lambda, where M might start to be ill-founded. So we're going to need, kind of like in the previous theorem, but different, we're going to need some kind of absoluteness argument, this time using raylessness of the tree, and the fact that the domain tree T is in the well-founded part. So that's what I'm going to do on the next slide. So recall, I'm just restating the situation here. We want to show the codomain M of the generic J thinks there's an embedding from T to J of T. Okay, so let's choose a root just arbitrarily of T. And then we have a notion of tree order. So then we can say TV is the tree above any given vertex V. And we can go then in a sense by induction on vertices using raylessness. So since T is rayless, so it has no infinite branch, we can show by reverse induction, I mean kind of on the reverse of the tree order. So starting with leaves, we can show that for every vertex, the model M thinks that there is an embedding from TV to the corresponding part of JT, that is JT above J of V. Now, this is completely trivial when V is a leaf, right? That's the base case. Because when V is a leaf, then this tree and this tree are both just a single vertex. So that's trivial. And on the other hand, we're done when the vertex V is the root, because then we have an embedding here from all of T to all of J of T. So we just need to then deal with the inductive step. So if it's true for all children of a vertex V, we want to show it's true for V also. So we take a well ordering of the children of V. This part is kind of like the previous proof. And then we proceed by recursion along that well ordering and kind of preserving, maintaining the order preserving property as we go along by mapping each child U of V to the least thing that it makes sense to map it to, the least thing that maintains the order preserving property, and the least thing that makes sense to map it to in the sense that M satisfies there's this embedding here. So the induction hypothesis says that for every child U of V, we have some embedding like this. We just need to put them together in a way which is overall an embedding, so overall injective, and we guarantee injectivity by preserving the order, which is stronger than injectivity, but the point is it allows us to maintain order as we go along. Okay, so that's my sketch that 1 implies 2. And to prove 2 implies 1, again, we have to take a bit of a detour through labeled trees. And we're going to show now, well, some of this is basically already done, but we're going to show the following statements are equivalent. The first 4 are like analogous to in the previous proposition with 4 things. So the new thing really is 5. So so we showed that 1 implies 2, but going through the large cardinals. Clearly 3 implies 4 again, because every embedding is a homomorphism. 2 implies 3 is like before, just we proved it without rayless, but you can see that it works if the trees are rayless. And 5 implies 1 is like 4 implies 1 before, we just proved it without the W here. But the argument is the same using the typed trees. So the new thing is that it remains to show that 4 implies 5. So let me just sketch that on the next slide here. Weak Vopenka's principle for 2 labeled trees with homomorphisms, that follows from VP for 2 labeled rayless trees with homomorphisms. So again, this is the correspondence between this weak here and this rayless here, which I mentioned as being somewhat surprising. Okay, so okay, this is the last slide that has technical details, and then I'm almost done. And whoops, I didn't mean to do that yet. So to show VP for 2 labeled rayless trees implies weak VP for 2 labeled trees. Take a sequence of 2 labeled trees such that they satisfy the hypothesis from weak Vopenka's principle of the existence of backward homomorphisms. And then we want to show that there's a forward homomorphism, which may as well go from just 1 tree to the very next one. So from some T alpha to T alpha plus 1, that's what we'll show. Now, the existence of such a homomorphism is equivalent to the existence of a winning strategy for player 2 in the following game. And by the way, some of the earlier things I mentioned in this talk could also be done using games, because generic Vopenka's principle can be formulated using games. In a sense, that's simpler than the actual definition using forcing. But I didn't want to talk about games before, but now I think I have to talk about games. So to have this homomorphism here, so it's equivalent to the existence of a winning strategy for the second player in the game where player one plays a path from the root in the first tree, and player two plays the path from the root in the second tree, I mean, they each play one vertex at a time, and player two is responsible for matching the labels at each step. So, by the way, if the two trees here have the roots have different labels, then player two is out of luck. Player two just loses immediately in that case. But in general, player two is trying to match the labels of the vertices played by player one as they both continue outward from the root in some direction. And this is a closed game for player two. If player two matches the labels correctly, successfully every time, then player two is considered to win. So now, if there's no such homomorphism, then by Gale Stewart, player one has a winning strategy. In fact, a canonical winning quasi-strategy just to always decrease the ordinal rank. So in other words, if player one has a mate in omega plus 37, just to use chess terminology, then that means on the next move, he or she should be able to place so as to have a mate in 36, omega plus 36 or below. And then, okay, then that ensures that player one always wins in finite time, right? Because there's no infinite decreasing sequence of ordinals. So now we can use this to define a rayless tree, right? So let T star alpha, it's going to be rayless. It's the game tree, that is just the tree of all positions in the game following one's winning quasi-strategy. Now, it inherits labels from the original trees in a natural way, so I'm not going to talk about that part. But the important thing is that it's rayless. Why is it rayless? It's rayless because there's no infinite play in this game if player one follows his or her canonical winning quasi-strategy, right? Because for player one to win, the game must end. Because it's a close game for player two. So for player one to win, the game must end in finite time. So that's how you get a rayless tree here, is by considering these game trees. And then if you apply Vopenka's principle for two labeled rayless trees to these T star alphas, then you can show that you get a contradiction. Maybe I won't discuss that part, but I just wanted to talk about where did the rayless trees come from in the first place. And it's from these game trees.
Trevor, I think I missed something obvious. Where did you use the assumption that you have the downward homomorphisms?
I didn't use it yet. That's to show that this is a counterexample, because, so I should say something about that. So say we have a homomorphism from T star alpha to, sorry, my handwriting with the mouse is so bad, to, by Vopenka's principle for rayless trees, all we know is it maps to some T star beta. It's pretty easy to see that you can take beta to be greater than alpha, right? Vopenka's principle may as well always give you maps going forward. You can show that. But the point is that beta might be much larger than alpha, whereas to get a contradiction, see, we used alpha and alpha plus 1 here in defining this, this game tree here. So to get a contradiction, we have to then compose this with a backward homomorphism to T star alpha plus 1. And then the point being that this composition of homomorphisms can be used to produce an infinite play in the game, to allow play. This homomorphism kind of informs how player 2 can play to last forever in the game against player 1, getting a contradiction.
Okay, I think I have an idea. Thanks.
Sure. Okay, so now on the last slide, I'll just summarize things and raise a few questions. So to summarize, we identified 4 kind of levels of large cardinal strength in decreasing order. They're VP omega and weak VP. I should say, so in the first 2, it doesn't actually matter if you say omega there. I just did that for convenience, right? And then the other 2 are generic VP omega. Here it does matter. And generic weak VP omega. And then these 4 levels correspond to, on the right, these 4 large cardinal principles. Basically, the W corresponds to strong instead of extendable, and the G corresponds to virtual. I mean, it's only an accident that they're different letters. Generic and virtual mean the same thing here. So what we showed, the first main theorem was that VP for trees is at level 3 of this hierarchy here. And by the way, there's another thing there. So actually many other things. A representative example would be locally planar graphs. They're sufficiently tree-like. So these are just graphs where every finite subgraph can be drawn in the plane. And so graph theorists have ways of showing that various classes of trees are sufficiently tree-like that tree-based methods apply to them. And so then using that, you can show VP for locally planar graphs also has this level of large cardinal strength here. And then we also, the second thing we showed is VP for rayless trees lives here at level 4. And again, you can use some graph theoretic stuff to show that VP for rayless graphs in general, just any graph without an infinite path, VP for those lives at level 4 also. So some natural questions I think are, first you could ask, well, what else, what other instances of VP, that is for which other structures, lives at levels, I should say levels 3 and 4. And then another thing is, I didn't have any new results in this talk about level 2 here, weak Vopenka's principle. So one could ask, is there a natural class of structures for such that VP for those structures, like maybe there are particular kinds of graphs that are more complicated than trees, but simpler than general graphs, and VP for those structures has this level of strength, namely an A strong cardinal for every A. Because here, the weak in WVP, of course, it doesn't mean we're limiting the kind of structure. It just means we're changing the principle by talking about backward homomorphisms. But can you accomplish the same thing by limiting the structure instead? And then, actually, maybe the most important question is, are there any other levels here that you can get in this way? I should be a little more precise to exclude some things. You can always talk about, Bagaria has studied different levels of definability, like Vopenka's principle or generic Vopenka's principle for pi n classes corresponding to, like in the generic case, n remarkable cardinals. That's another way to weaken it and get, in fact, infinitely many intermediate principles. But I really just mean other levels in terms of, well, natural classes of structures instead of trees or graphs or rayless trees or rayless graphs, etc. Okay, so I'll stop here.
Very, Trevor, thanks very
Thank you.
much. This was super, super interesting. This was great.
Thank you.
Any questions?
Oh, I have a kind of question. Back at the very beginning, you had structures labeled S that were being compared to structures labeled T. This is like your first theorem. And the structures labeled S, you had certain well-founded relations. And then you had these embeddings or whatever to mappings to structures labeled T. And you had structure, you had relations on the guys in the second, right? Now, R less than or S is well-founded, but is less than T assumed to be well-founded?
Yes, in this instance, because, yeah, so this is a bit different than in the proof of the second theorem, where we use the weakly virtually strong cardinals. In here, we begin with a proper class of trees, and then for each one, we simply choose this well ordering. And oh, I did need to mention, this appears to use global choice, and you can get around that. But we simply chose the relation in this case to be well ordered.
Mm-hmm.
Yeah.
So, okay,
Sorry.
so the one on the right, the T one is also well ordered.
Yeah, because they were just chosen in the same way. So you just, we defined a whole class of these things.
Oh, gotcha.
So Trevor, you said that, yeah, I was wondering, because this did appear to use global choice, which you didn't mention at the beginning, but you're saying that you can get around it, right?
Yeah, so let's see, what's the easiest way? Well, the one way to get around it would simply be, instead of using GVP omega, simply use the equivalent large cardinal principle. And if you do that, so the equivalent large cardinal principle says for every class, there's a weakly virtually C extendable, say kappa, then you can limit your attention to just a tree of kappath least rank. And then you only have to choose one well order, namely of that one.
I see. Yeah, I think this makes sense. Okay, thanks.
And by the way, if you do it that way, I can relate it to the previous question. So if you do it that way, then you do have to use the fact that in the definition of weakly virtually A extendable, the domain is required to be fully well-founded.
More questions?
I can make a historical remark.
Go ahead, Ken.
Yeah, I met Vopenka only once. It was somewhere in Europe. As I remember him, he was very unlike, the rest of the set theory people running around. He marched to his own drummer. He was he had deep intuitions about the world of sets, that were really remarkable. And he was also very handsome. He was a very distinguished fellow. And he had, I hope he's still with us, and he had, of course, the checks would hang on his every word. He was, so it was, talking with him was an event, it was, but these intuitions he had, to me, the Volpenka is a kind of reverse, pigeonhole principle. It's remarkable that it works that way.
Well, I never met Vopenka in person, but I've read several times that the way Vopenka's principle originated was that he rather didn't like some of this large cardinal stuff and said, you guys can't even refute the following absurd thing. And well, it wasn't absurd. It turned out to be equivalent to some large cardinal axioms. Let me ask another question that's completely off to the side and not really about something I know anything about. But I've heard a lot in finite combinatorics about the notion of tree width of graphs. Does that notion make sense for infinite graphs? And if so, are there Vopenka principle for trees, for graphs of bounded tree widths?
Yeah, it's a good question. I considered that at one point. I have to take a moment to remember exactly what I decided. If I remember correctly, Vopenka's principle for graphs of bounded tree width is equivalent to generic Vopenka's principle. It's kind of like what I was talking about in this slide here with locally planar graphs and showing that they are in a sense tree-like. Now, I believe they do have low tree width, and that's kind of related to what I meant by tree-like. Really the main thing though is that they have normal spanning trees. I think that's sort of related. I kind of stopped thinking about tree width once I discovered this notion of normal spanning tree because it seemed more relevant, but it's also related to tree width, I think.
Thank you.
Anyone else?
When I think about the classes of graphs which are in between the class of all trees and the class of all graphs, I think about median graphs.
Sorry, what?
Median graphs.
Oh, and what are those?
I'm going to type it in the comments, but a median graph is graph where if you take any 3 nodes in your graph and there exists a 4th node such that and there exists a unique 4th node such that the shortest path between any of those 2 of the 3 nodes in your graph goes through the 4th node. So perhaps it's more clear if I type it in the comments. So
yeah, that might help.
Suppose that we have a graph. If AB are vertices, then let the interval between AB be the set of all nodes on the shortest paths between A and B. Then the median of 3 vertices ABC is the unique node in the intersection between of AB, AC, and BC.
Okay, yeah. So I'll have to think about that because this definition is not familiar to me at all. But thanks for the suggestion. And I just noticed your previous one about scattered linear orderings. That sounds like a good thing to think about also. So I haven't thought about linear orderings or posets much. I've really only thought about graphs. So I think linear orderings and posets would also be a good thing to consider.
Okay.
Thank you.
You're welcome.
Anyone else? All right, then Trevor, thanks very much again for your super interesting talk.
Thank you.
And I've given up on the clapping in this setting, so please post your reactions in any way you would like. And so for the next 2 weeks, we have Erin, who I think is here. She was one of the people asking questions. And so she will be speaking for the next 2 Fridays. I have title and abstract posted.
Yes, looking
Okay.
forward to it. Yeah.
Me too. All right.
All
So
right, thanks, Trevor. Great talk.
Thank you.
I guess I will see everyone next week.
Yep.
To see everyone.
Thanks, Trevor. That's great.
Thank you.